Hello, welcome to lecture 21 of Elec Eng2CI5. In this lecture, we'll discuss an approach for solving first-order systems or first-order circuits. These are the circuits that contain only one energy storage element, such as a capacitor or an inductor. The approach we'll discuss today is called the circuit approach, sometimes called the step-by-step approach. It is used under these two names. What it does is that it tries to make use of Thevenin equivalent to determine the time constant of the circuit, and then try to find the steady state and the initial conditions, and from which you can determine the complete transient profile. Let's take a look at this theorem, and we'll try to illustrate it through a number of examples. In the previous video and in other examples, we have seen a number of things. We noticed that, for example, when you have a circuit like this one, we have a capacitor. It initially had 0 voltage. You connect it through a resistor, and then when you close the switch at time 0, so if I close the switch here at time t equal to 0, what's going to happen? Current will start to flow from the source, okay, and then it will start to charge this capacitor. And if you have 0 initial conditions, so this capacitor did not have any voltage in the beginning, this is the expression that we were able to derive from the expression of the capacitor. You can see at time 0, this will give you 1 minus 1, so you get 0. At time infinity, this term will be equal to 0, and you get E, which is the battery value. So this capacitor will charge the battery value. If E is equal to 5 volts, then VC will charge to 5 volts in infinity. We say the condition at infinity is a steady state condition. We also can show exactly the same way if you have an initial capacitor, a capacitor that has some initial voltage. So VC of 0 is equal to some value, VC naught. It can be 1 volt, 2 volt, 3 volts. If you close the switch again at time 0, what's going to happen if you close this one at time 0, okay? What's going to happen is that current will start to flow from the source, and charge will start to accumulate on the capacitor until the capacitor is fully charged and there is no current in the circuit, and the capacitor will represent the open circuit. In this case, the VC of infinity will be equal to E, because this voltage here must be equal to this voltage here, so that there is no current flowing in the circuit. Okay, so if the E is 5 volts, VC will charge to 5 volts. The expression for this one can be written by this one here. You see, when you put T equal to 0, this becomes 1. Minus E will cancel with E, will give you VC0. So VC0 here can be non-zero value. But when T goes to infinity, this term goes to 0, and this bracket will be 0, and then you end up with E, which is the battery voltage. So here you can see the capacitor is charging from an initial value of VC naught up to E. One other example we tried before is they have a capacitor that's charged, and then you connect it to a resistor or 2 resistors. This is charged. So now this one is connected to R1 and R2. It will start to allow current to go through in the circuit, okay, and it will be losing its energy gradually and slowly. Its voltage will be decaying with time, and you see that the expression here is VC naught e to the minus t over tau, and tau is the time constant equal to the total resistance multiplying C. So tau here is R1 plus R2. In all these examples, and even examples with inductors, you will notice something very interesting. You will notice the solution is always a constant plus another constant multiplying e to the minus t over tau. This one here is a constant plus another constant e to the minus t over tau. Remember, VC naught is the initial condition, it's a number. E is the battery value, it's a number. So this will give you a constant plus another constant e to the minus t over tau. This one here is a constant e to the minus t over tau. So this allows us to put a general template for any circuit containing a single element, a single energy storing element, like a capacitor or inductor. So let's see this form, and then once we have this form, we'll try to find its coefficients by imposing initial conditions, by imposing steady state conditions, and by finding Thevenin equivalent looking from the side of that energy storing element. So, as I explained in the previous slide, all the solutions are given by K1 plus K2 e to the minus t over tau, and the only difference K1 and K2 and tau. We have here 3 unknowns, these 2 constant and this time constant. Well, if you take steady state response, so when t goes to infinity, this term becomes 0, and this x of t, which can be a voltage of a capacitor or a current of an inductor, x of infinity, which is a steady state case, will give me K1. So K1 is a steady state response, okay? We can calculate this steady state response by making all capacitors open circuit and by making making the inductor in the circuit as a short circuit, okay? So we can find K1. K1 is the steady state response. Simply take the limit as t goes to infinity. We allow the circuit to be in its setting for a long time. So x of infinity will be K1. Okay, how to find K2? Well, we need initial values. So in the beginning at time 0, we need the current of the inductor at time 0 or the voltage in the capacitor at time 0. X here may represent current or inductor voltage in a capacitor. So if you put t equal to 0, you get K1 plus K2 e to the power 0, which is 1. So K1 plus K2 is equal to x of 0. Okay, and this symbol 0 plus means it is the value of x immediately after the circuit started operating. So there is 0 minus just before the circuit started operating and 0 plus just after the circuit started operating. So K1 and K2 already know what is the value of K1. This is a steady state response. So this x of infinity. So we can simply say that K2 is x of 0 minus x of infinity. It is the initial value minus the steady state value. Now, how do we find tau? Tau is a time constant. And we find it by building a Thevenin equivalent from the side of the element. For example, if you have a capacitor, and this capacitor looks something like this, I'm going to find the Thevenin equivalent looking into this capacitor. Okay, from the capacitor side. So I found R Thevenin, this one here, this resistance here will be R Thevenin, and this one will be V Thevenin. So the charging time or discharging time will be equal to R Thevenin C, as we explained earlier. Okay, this for a capacitor. If this was an inductor, the charging time or discharging time constant, it will be L. It's actually L over R Thevenin. It should be L over R Thevenin here. Okay, it's not R Thevenin over L. It's L over R Thevenin. Okay, let's start to take a look at some examples. The theory is actually pretty simple. We have three constants, K1, K2, and tau. We have to find them for any circuit, and then we have the expression for the capacitor charging or discharging, for the inductor charging, discharging. Let's take a look at this circuit here. Before time t equal to 0, this switch was opened. Okay, and at time t equal to 0, this switch got closed. Okay, so before time 0, the circuit was already at steady state. So you have this inductor here short circuit, okay, and then we can find what we call I of 0 minus, the current that was flowing in the inductor just before this switch was closed. Okay, so what we're going to do, we're going to redraw this circuit. The switch is now still opened. Time t did not come yet. Okay, and then we have this 6 volts, we have these three resistors here, and we have the inductor, and the inductor is short circuit because we assume that the circuit has been running from minus infinity up to 0, and at 0 we had this switch closing. So if you draw the circuit, you have to make this one short circuit, and our target now is to find IL at that time. This IL is really our initial value that we are going to be using when the switch gets closed. Okay, so before the switch is closed, S is closed, this is how things look like. There is no 6 ohm here because the switch is opened. The inductor looks like a short circuit, and now my target is to find the current flowing the inductor IL. So just to correct here that this one here is IL. This current here, okay, this is really what I call IL. I call it here I, but it's effectively IL. Okay, so this current is not that difficult to see. That the current supplied by the circuit or by the battery here, this one here is IL, and this current here will flow in the two parallel branches. It will split, and then it will recombine again. So this current here, the current flowing here is the current supplied by the battery, and this equal to the 6 volts divided by the equivalent resistance. It's not that difficult to see. The equivalent resistance here is equal to 6 in parallel with 3. 6 multiplying 3 over 6 plus 3 will give us 18 over 9, will give us 2 ohms. So R equivalent is equal to 2 ohm. So this was the current flowing in the circuit just before we close the switch. This is why I call it IL of 0 minus. Okay, very important to understand. This was the current, the steady state current flowing in the inductor just before the switch was closed. Okay, now because the current inside the inductor cannot change instantaneously, as I explained before in lectures, this current will still be the same value, will have the same value even immediately after the switch is closed. So IL of 0 plus is equal to IL of 0 minus. The current flowing here just before the switch was closed is equal to the current flowing here just after the switch was closed. And both of them have a value of 3 ampere, which is 6 volts divided by the equivalent resistance here, which is equal to 2 ohm. Now we consider the second stage. We close the switch. Okay, so the 6 ohm was added to the circuit. The current flowing here at time 0 plus is equal to 3 ampere as we agreed. Okay, now my target is find the constants k1, k2, and k3 and so on. But before I do that, I need, of course, as I explained before, I have already the initial conditions. I have IL of 0, IL of 0, 3 ampere. So this is the current that was flowing in this inductor just after the switch was closed, okay? So we know IL of 0, 3 ampere. We need IL of infinity. This is a steady state value of the current after the switch has been closed, okay? So here the inductor will look like a short circuit. Okay, I'm still keeping it in its form, but I know I'm doing DC analysis because I'm talking about steady state. So this one here will be short circuit. So my target is to find the current flowing here at short circuit, at steady state, when this short circuit at steady state. This current, as you can see, is equal to I3 plus I1. Then my target is to find I3 and I1 and this current I total. So this I total will be split into I2 and I1. I2 will be split into I3 and I4. Okay, it's not that difficult. First, if this is short circuit, you see that 3 ohm in parallel with 6 ohm, so this will give me 2 ohm. This 2 ohm is in series with 3 ohm, so it's going to give me 5 ohm. Then the total resistance seen by the circuit is 5 ohm in parallel with 3 ohm. Okay, this is what I have here. 3 multiplying 5 or 3 plus 5, this will give me 15 over 8 or 1.875 ohm. So the total resistance seen by this 6 volts is equal to 1.875 ohm. Then I can find this current I total. This is very simple circuit analysis. And you notice I'm taking now, assuming that the inductor is short circuit, because I'm talking about a steady state condition for the case after the switch has been closed. Okay, I total is equal to this 6 volts divided by the total resistance 1.875. This will give me 3.2 ampere. This 3.2 ampere will split into I2 and I1 according to current division ratio. Remember that the resistance of this branch is 5 ohm, 3 in parallel with 6 in series with 3. This is 5 ohm and this is 3. So I can get I1. I1 is simply, or I2, doesn't matter. I2 is equal to 3 over 3 plus 5 multiplying this I total. And this is what I have here. Okay, I total, we already calculated I total. I total is 3.2. So I'm going to take multiply this by 3 over 8. This will give you 1.2 ampere. So this is 3.2 ampere. We found this one. This one here is 1.2 ampere. So we know that I1 is equal to 2 ampere. Okay, so this is 3.2. It's split into 1.2 here and 2 ampere here. Okay, now we have to split I2 again because the current I'm looking for is I3 plus I1. Okay, this current I2 will be split between these two resistances. I can get I3 is equal to 6 over 6 plus 3 multiplying I2. So this is what I wrote here, that the current I3 is equal to I2 multiplying 6 over 6 plus 3. Because the division ratio here, if I want to get this current, will be 6 over 6 plus 3. And this multiplying I2. Okay? If you do this one, you get 0.8 ampere. So we know the current here is 0.8 ampere. So we have here 0.8 ampere flowing this way. This is I3. And I have I1, which is equal to 2 ampere. Then I know that the steady state current of the inductor is equal to the sum of these two is equal to 2.8 ampere. So I know now the initial current of the inductor. We already calculated that. We know the steady state current of the inductor. We calculated IL of 0 and we calculated IL of infinity. IL of infinity here is equal to I3 plus I1, as I explained earlier. It's equal to 2 plus 0.8 is equal to 2.8. So we know that the inductor current, steady state inductor current is 2.8 ampere. Now the last step in our calculation is to find tau. Before I found out, I wrote the expression for IL. We know that at time t equal to 0, we had the current 3 ampere. This is what we calculated from the first stage when the switch was open. So 3, if you put t equal to 0 here, you get this becomes 1. So you get k1 plus k2 is equal to 3. We also calculated that at infinity, if infinity, this term becomes 0. So k1, which is the current at infinity, will be equal to 2.8 ampere. So we know that the expression for the inductor current is 2.8 plus 0.2 e to the minus t over tau. Okay, what is tau? Tau is the time constant. Time constant seen from the inductor side. It's L over R Thevenin. I kept this side open because I would like to calculate the input resistance seen from the inductor side. So I want to find R Thevenin looking from here. Of course, the way we do it, we remove all the independent sources. So I'm gonna short this one out. Okay, and then when you do that, you'll see that the equivalent resistance seen is not that difficult to see it. You have 3 here, and it's series with 6 in parallel with 3. So this is gonna give me 5. This will give me 2, and in series with 3 will give me 5. So 5 in parallel with 3. So 5 by 3 over 5 plus 3, you end up by 15 over 8. Then the Thevenin, the time constant for the charging or discharging of this inductor, it's L over R Thevenin, and I am repeating this is L over R Thevenin. I had a typo in the previous slide. L is given to us as 2 Henry, the value of the inductance, and R Thevenin is 15 over 8. So if you do that, you get 16 over 15 seconds. So now we can find the total answer for the inductor current is 2.8 plus 0.2 e to the minus 15 over 16t. So at time t equal to 0, this become 1. The initial current is equal to 3 as we calculated. At time t equal to infinity, this term goes to 0, this term will disappear, and you have 2.8. So the inductor current is actually going down from 3 ampere to 2.8 ampere at infinity. And the time constant for this discharging is tau, which is equal to 16 over 15. This is e to the minus t over tau. Okay, so remember at minus infinity, here the switch was opened. Then the inductor took its time until the current built up to its value, which is 3 ampere. But this 3 ampere serves as the initial value for the second stage when the switch got closed. And this is what we're going to use, 3 ampere, and the steady state here is 2.8. So we found the initial value, we found the steady state value, and we found the time constant. Then we solved the circuit. Okay, we move to see this example here. In this example, we have a capacitor and we have 2 batteries. So we have this switch here. Before time equal to 0, the switch was closed. So this was connected, and we have both the 6 volts and the 12 volts are on the circuit. At time t equal to 0, this switch opens, and this 6 volts gets out of the circuit. Okay, so what we're gonna do, we're gonna first try to find the expression for Vc of t, and notice that what's required is not Vc of t, it is V naught of t, but we'll get this one as a byproduct after we solve for the capacitor voltage. Okay, so let's see how we can do that. I will, at the first stage, when the capacitor has been, when the switch has been connected or closed for a very long time, the capacitor will represent open circuit. So I'm gonna redraw the circuit again with this capacitor open circuit, and then I will try to find the voltage across it. This will give me the steady state in the first position for the capacitor when the capacitor is shorted, and this steady state of the first stage will serve as the initial condition for the second stage when the switch is opened. Okay, so let's see how we're going to do that. I redrew the circuit again. I made the capacitor open circuit, okay, because we are now and the switch is closed. You can see the switch is closed here, so we are still in the first stage. The switch is closed, and we would like to find the initial voltage across the steady state voltage across the capacitor, which will serve as the initial voltage for the second stage when the switch is opened. Okay, so for this circuit, it looks a little bit difficult, but it isn't really, because the voltage between here and here is equal to 6 volts. Okay, So you have here 12K and you have here 8K, and the voltage between here and here is 6 volts. The same currents flowing in both of these, so this acts like a voltage divider. Okay, so this voltage here relative to ground, this ground here is equal to 6 volts, and these two resistances are in series. Then I can simply say that VC is equal to this voltage multiplying 12 over 12 plus 8. So the voltage division here is 12 over 12 plus 8. So this is the capacitor voltage just before the switch was opened. And it is going to be also the capacitor voltage just after the switch was opened, because as I explained before in lectures, the capacitor voltage cannot change instantaneously. It needs some time to change. Okay, so once you open the switch, this will also be your initial value for the next stage. This one here is 6 volts. Multiply 6 by 12, you get 72. 72 over 20 will give you 3.6 volts. So now we're going to do the second stage. Second stage, we're going to remove the source because the switch is opened, and then we try to find the steady state condition for the second stage. So remember, we have now initial condition. We're looking for the steady state for the second stage when the switch is opened. Okay, so this is what we did. We opened the switch. The 6 volts battery is gone. It's not there in the circuit anymore. I would like to find the capacitor voltage at steady state. This is a circuit here. This battery, maybe it's injecting current. The capacitor is charging at steady state. The capacitor is fully charged. No more currents going through the capacitor. This represents open circuit. So we're going to replace the capacitor by open circuit. Okay. So you can see here we have here one loop. Even though I'm showing the capacitor is still there, but when I do my calculations, I'm actually considering this one to be open circuit. So we have only one loop. Okay, 12 volts in series with 12K, in series with 8K, in series with 4K. And the capacitor voltage is across the 12K. So this is a voltage divider. So I can say that the capacitor voltage at steady state is equal to 12 volts multiplying 12K over 12K plus 4K plus 8K. Okay, so if you do this calculation here, you see that the capacitor voltage across this open circuit capacitor, okay, which is the capacitor voltage at infinity, is going to be equal to 6 volts. The second step, I did all the steps really without having to make any redrawing because it is a very simple circuit. If I want to calculate the Thevenin equivalent seen from the capacitor side, what I'm going to be doing, I have these my terminals here. I will assume that this is gone, this open circuit, and I would like to find the Thevenin equivalent seen from this side. Okay, of course I'm going to replace the voltage source by a short circuit. And if you try to find the input resistance seen between these two terminals, it's not that difficult to see. It's 12K in parallel with another 12K. Okay, so it's 12K in parallel with 12K 6K. So we know that the Thevenin resistance from the capacitor side is 12K. We know that the time constant through which the capacitor is charging or discharging is R Thevenin multiplying C. I write it as R, but it's really R Thevenin. So it's 6K, 6 10 to the power 3. This 100 microfarad. So this will give us 6 to the power 5, 10 to the minus 6. You get 0.6 seconds. Then the expression for the capacitor in this second stage is K1 plus K2 e to the minus t over 0.6 seconds. Okay? So now my target is to find K1 and K2. Actually, we have all the information we need to find K1 and K2 because we know what is the initial value. So if you put t equal to 0, initial value will be equal to K1 plus K2. If you put t equal to infinity, you get the steady state, and K1 is equal to the steady state, which is equal to 6 volts. So by doing so, I'm able to get K1 and K2 just by solving the initial value and the steady state value. So we tried before that the initial value, VC of 0 minus equal to VC of 0 plus, is equal to 3.6 volts. This will give me K1 plus K2, plus this term is multiplying e to the 0, which is 1. Now, if you put t equal to infinity, the term e to the minus infinity will give us 0, so this is going to be gone. You have only K1, so K1 is 6 volts. K1 plus K2, 3.6 volts. So it's obvious that K2 will be negative. It's going to be minus 2.4 volts. So this is the expression for the capacitor voltage. It is 6 minus 2.4 e to the minus t over 0.6 second. So this all in volts, but this one here is in second. So this is how the capacitor looks like. At time 0, it starts by 3.6. And then gradually and slowly it charges up to 6 at infinity. Okay? and the time constant through which charging is this 0.6. Remember, the 0.6, the time constant determines how fast the charging or discharging is happening. So after 1 tau, it goes up to 0.6 of its peak of the difference between here and here. Okay, so this really determines how fast your capacitor is charging or discharging. It's charging here in this case. The last thing we'd like to calculate V output of t. Well, if I know Vc at a function as a function of time, I know everything in the circuit. Why? Because if I know that this is Vc, then I know what's Ic. Ic is equal to C dVc by dt. Okay? And if I know this Ic, I know if I know Vc, I know also this voltage here, this current here. This current is equal to Vc divided by 12K. So the current flowing through this 8 kilo ohm is nothing but Ic of t plus I of t. This one here is C dVc by dt, and this one here is Vc over 12K. And when you sum these two currents, you obtain this current here I naught, you multiply it by 8K, and you get V output of t. I did not simplify it, I simply wrote the two terms. So this one here is Vc, this is the one we calculated earlier. I divided by 12K, so this will give me this current. This one here is C, is 100 microfarad, 10 to the minus 4, multiplied by the derivative of this term. If you differentiate this term related to C, you get minus 1 over 0.6, so this will give you 4, e to the minus t over 0.6. Of course, you can collect the corresponding terms, and you should take into account this divided by 12K, and then you multiply everything by 8K. So this will give you the value of the output voltage as a function of time. As I mentioned in class, the Kirchhoff current law and Kirchhoff voltage law do apply for transient analysis for time varying signals at any time. Okay, so this is what I did. I found this one at any time t, I found this one at any time t, I summed them using KCL, and I found this current at any time t, and then I said that the output voltage is equal to this current multiplying 8K. Of course, you can simplify this expression and obtain a much simpler expression if you want to. Okay, let's try one last example. We have this circuit here. We have a switch that has been closed for a long time. So what's happening? This battery supplied some current through to all the circuit, okay? And then at time 0, we suddenly open the switch, and as a result, there is no source really connected in the circuit. And as we have learned from our previous examples, the inductor will be charging the first part, the current through it to be established, the magnetic flux through it to be established, and when this source disappears, it will start to supply energy and current to the rest of the resistances, and this will result in it losing all its energy gradually and slowly with time. Our target again is not to find IL of t, the current flowing through the inductor, but rather to find V naught of t. And as we will see, once you have found the inductor current or the capacitor voltage, all the other quantities are really a byproduct of these, and you can calculate them very easily using KCL or KVL. Okay, so before the switch is open, the circuit has been in this position for too long. Then the inductor reached steady state, and now it represents short circuit. Okay, and our target is to find this short circuit current, the current flowing in this inductor, because this steady state current of the first stage will serve as the initial current of the second stage when the switch is opened here and this battery is disconnected. Okay, so this is what you have to do. If for something like this, it's obvious that these two are in series. Okay, 6 and 6 are in series, they are in parallel with 6, and this branch is in parallel with this one, is in parallel with the short circuit. So the short circuit eliminates this whole thing here, it's not there. So any current flowing from the source will go as 2 ohm this way and 2 ohm this way, and the rest of the circuit is not going to get any current. Okay, then the current flowing, what is the equivalent resistance seen from the source side? You have 2 ohm in parallel with 2 ohm, it's 1 ohm. Then the total current supplied is 12 over 1 ohm, so this will be it's 12 ampere. This 12 ampere will be split equally between this 2 ohm and this 2 ohm. Okay, nothing is going to reach the other circuit because this short circuit eliminates this one, this branch, and this branch. So the current flowing in the inductor at time 0 minus 6 ampere. Just before the switch was opened, the current was equal to 6 ampere. And as we explained in class, the current through an inductor cannot change instantaneously. So once you open the switch, we know that the current immediately after the switch was opened will still be equal to the current immediately just before the switch was opened, and is equal to 6 ampere. Okay, so now we know the initial value we are going to use in the second stage. In second stage, we don't have this battery anymore, this is connected, and we're going to redraw the circuit again and then try to find the expression for the current flowing through the inductor. Okay, I redraw the circuit here. I still keep the inductor there, even though I know that at steady state it's going to be a short circuit, but this is fine. Of course, if you take a look at what's happening, this one has some initial current, and this current has been established from stage 1 when the battery was there. After the battery is removed, the inductor will start to supply power to all these resistances, and gradually and slowly it's going to lose all its energy. So we know that at infinity, there will be no current in the inductor. Okay, it's going to be completely discharged. It lost its magnetic field completely, and then this is what we know. Now, so we know the initial current. We already calculated this initial current from the previous slide. Now we are already calculating as well the steady state current is equal to 0. The Thevenin resistance seen between the inductor terminals, what you have to do, you have to create an open circuit between these two terminals here, and then to find the Thevenin equivalent. What I did, I combined this 6 ohm with this 4 ohm because these are in parallel, and this gave me 2.5 ohm, 2.4 ohm. So this 6 ohm here, you can see it's joining this point and this point, and this branch is joining this point and this point. So I replaced them both by 2.4 ohm. So this is how the inductor look like. It's supplying current. Part of it will go to 2.4 ohm, part of it will go to 12 ohm. Okay? So the Thevenin resistance seen between the two terminals of the inductor, if you remove the inductor and take a look at the circuit, because we don't have really any sources anymore, the equivalent resistance seen here is 12 ohm in parallel with 2.4 ohm. Okay, so it's 12 ohm multiplied 2.4 over 12 ohm plus 2.4, and surprisingly this is going to give us a rounded number which is 2 ohm. Okay, so that we know that the Thevenin resistance seen between these two terminals, between the terminals of the inductor, is 12 ohm in parallel with 2.4 is equal to 2 ohm. So now we can calculate the tau as well. We know that steady state current is 0. We have the initial current we calculated from the previous calculation, and now we are ready to find the full expression for the inductor current. Okay, so the time constant for an inductor is L over R. The inductor is 1/4 of a Henry divided by 2. This will give me 1/8 of a second. Then the expression for the inductor current is K1 plus K2 e to the minus T over tau. Remember in the beginning we said when you put T equal to 0, we found that the initial stage will be equal to 6 ampere. But when T goes to infinity, we found out that the current will be equal to 0. So K1 will be equal to 0. Because if you put T equal to infinity, you get K1. And we know that steady state current, the inductor lost all its energy. It does not have any current anymore. So K1 is equal to 0 and K2 will be equal to 6 ampere. So the expression for the inductor current is 6 e to the minus T over tau. Tau is 1 over 8, so e to the minus 8t. Now, I know the current flowing here. This is the expression for the current. This current will be divided between a 12 ohm resistor and a 2.4 ohm resistor. So if I want to get the output, I'm going to find the current flowing in this branch, and I'm going to multiply it by 6 ohm, and this is going to give me the V output. Okay, and this is what I did. I have the inductor current, I already calculated it. It's a function of time. I will multiply it by 2.4 over 2.4 divided by 12. Remember, if I want to get the current flowing here, I have to use a ratio of 2.4 over 2.4 plus 12. It is the opposite to the voltage division. Okay, and then you multiply this by 6, and here I multiplied by minus 6. Why? Because the current flowing, if this is the inductor current, then the current is going to push in the circuit is this way, and this current create an output voltage with this polarity. So this is why I have to include the negative sign. Okay, so this is why I added here a negative sign of minus 6, because this current is actually flowing not from positive to negative. The output is flowing from negative to positive, so I multiplied by minus 6. Surprisingly, again, this number is going to give us minus 1. So 6 by 2.4 has the same value or as 2.4 plus 12. It's 14.4. So this will give you minus 1. So the output voltage have the same expression as the inductor current multiplied with a negative sign. So this is the inductor current, and this will be the output voltage. It's minus 6 e to the minus 8t.